Of this chapter, I said we should learn 4 definitions. Well, first one is defined. Well, that's the first thing we learn. The next thing is the limit, and then it gives us the continuity. And the last one I said is differentiability. Differentiability. Okay, now I'll tell you the relationship between them. When a function is defined, or let's say from backwards, it's with increasing levels. If I said a point is differentiable, okay, if I said a point is differentiable, then it must be continuous. Then it must be defined and limit exist. Okay, I can go backwards. If the last one exists, which is true, differentiable, then it must be continuous and must be defined and limit exist. But if I said at the point is limit exists and limit exists and is defined, not necessary to be continuous. Okay, not necessary to be continuous. Well, to prove it is continuous, I need extra thing. Which is the defined is equals to the limit. Remember? Defined value needs to equals to limit value, then it's continuous. But if I said it's continuous already, the limit must exist and it must be defined. Okay, otherwise it can't be continuous. And then if it's differentiable, well, I need some extra thing here as well. So I'll talk about what we need. We need another information. So you know this point is continuous, but you can't make sure it is differentiable or not. Okay, it can be differentiable. If it's differentiable, it must be continuous. If it's continuous, must be defined and limit exists. But if you go from the left hand side to right hand side, you need additional information. Okay, that's the relationship between those 4 definitions here. Okay, so let's talk about the differentiability. What is differentiable? If a function f is said to be differentiable at x equals to a, if the limit exists, okay, if you can define, well, basically this means if you can differentiate that point. But what point cannot be differentiated? Okay, that's the thing we need to worry about. What point we cannot differentiate? So in general, a function is not, this, I don't really like what I'm writing before here. So I want to make a new chart here. So what is not differentiable? Okay, this is tell you what is not differentiable. So first of all, if you know a point is not continuous, okay, if you know a point is not continuous, you know, like you can see from the graph, there's a jump, horizontal jump, vertical jump, open circle, they're all not continuous. The graph is not connected. Then that point is not differentiable. So, okay, for what reason the point cannot be continuous? There might be 2 reasons. When there's open circle, when it's not defined, or when the limit does not exist. Okay, when it's not defined or the limit not exist, and then it's not continuous. So you can see from a graph that is not continuous. Then you know it's not going to be differentiable at that point. But what point might not be continuous? When it's not defined, when the limit not exist. What time? At which situation limit will not exist? Horizontal jump, vertical jump. Okay, horizontal jump, vertical jump, the limit might not be exist. When it's not defined, open circle, you don't have a y value, not defined. That's the first case when it's not differentiable. Second case, okay, that's the first case. Second case is the endpoint. Okay, endpoint. Regardless whether the endpoint are inclusive or exclusive. Okay, see the point I have? Regardless whether it's inclusive or exclusive, the endpoints will not be differentiable. Okay, you can't differentiate the last point of your graph. Say we have left hand side, right hand side, is not differentiable. Okay, so endpoint will not be differentiable. So no reason that's because I only have right hand side, I don't have left hand side, so I can't compare left hand side and right hand side. So that's why it's not differentiable. It will make much more sense when I talk about the third point. The third point, well, the third point is like, they said it's a sharp point or a cusp, like something, well, I say it's a sharp change of direction, or sharp point of like this. Okay, if this point is not differentiable, how I can reason this, why it's not differentiable? Like, you may ask me, what kind of change is a sharp change? What kind of change is not good change? So overall, I can say left hand side derivative is not equal to right hand side derivative. Can you see that's too linear like this? Okay, left hand side, the linear got the negative gradient, right? Right hand side, linear got the positive gradient. Well, same point. See from two sides, you got two different gradients. Which one we should take? Don't know. So not differentiable. Okay, not differentiable. Well, you need to see the same point on both graphs. If on the left hand side and right hand side not going to give you the same value of the differentiable, like the gradient, so it's not differentiable then. Okay, so that means a sharp change. The change of direction is not smooth. Okay, change of direction is not a smooth change of direction. So a sharp point is not differentiable. It is continuous point. Okay, it is continuous point, but not differentiable because of like a change of direction. Okay, suddenly change of direction. So three cases, one point will not be differentiable. First, when it's not a continuous point. Second, when it is an end point. Third, when it's a sharp change of direction. Say left hand side and right side derivative are not the same. Those three situations, they are not differentiable. Okay, so let's talk about differentiability. So again, when we talk about continuous, the continuity for a function, we only look at the join point, right? Like where you connect your two functions, like x belongs to negative infinity to 2, and then right hand side is 2 to infinity. The point we want to investigate is the x equals to 2. Okay, x equals to 2. We see whether they have the same y value or not, and then to predict they are like continuous or not. So same as the differentiability, there's no point to talk about x squared, like which point is not differentiable. You know, like every point will be differentiable because it's on the same function. Okay, there's no change of functions. It will be differentiable everywhere. But let's say we have fx. Look at that hybrid function. We have fx belongs to negative infinity to a, and then a to positive infinity. The a is the connection point. Okay, we're two different functions trying to connect. Okay, trying to connect. Well, things can join in two different ways. They can join smoothly. They can join not smoothly. Okay, they can join in two different ways. They can join. Okay, join together. Well, this graph is joined not smoothly. Okay, so it's a sharp change. So if we see the first function, you sub a into the first function and into the second one, if they are equal, this gives you that they are joined together. Okay, they are connected. Therefore, it's continuous. It is continuous. Well, that's how we test about the continuity, right? When they have the same y value for the same x, which means those two graphs are joined together, then they are continuous. This is the continuous point. Okay, if it is continuous, it is joined together, then we go to investigate the next thing. The next thing is the derivative from both equations for the same point. Okay, we look at the derivative for the same point A on two different graphs. Okay, on two different graphs. If they are equal, which means they join smoothly. Okay, the gradient on the left and on the right give you the same value, which means they join smoothly. And then we can make the conclusion it is differentiable. Okay, it is differentiable. So if it's not joined together here, then you're not going to do the next step. Doesn't matter whether the gradient equals or not. They are not joined together, it's not differentiable. So you need to test about the continuity first. Okay, we need to say it is continuous. Okay, and then we talk about whether it's differentiable or not. Otherwise, there's no point to talk about the differentiability when it's not continuous. All right, let's have a look. The first example. Well, first example is quite easy. I'll skip the first one. If I have time, I'll come back to it. Let's talk about example 2 and example 3. They are very typical cases. Okay, hybrid function fx is joined by x squared plus 2x plus 1 and 2x plus 1. They trying to connect it at x equals to 0. Okay, at x equals to 0. So what I would say is, first we talk about the continuity. Well, I want to find f dash x. Okay, easy to find f dash x. Just derive them. What is hard to find? Well, easy to find rule. To find the rule. Hard to find domain. Okay, whether include 0 or not, whether include the endpoint or not, like which point should be excluded for the derivative. That's what you need to really they want to see. Everyone can differentiate that. 2x plus 2 and the bottom one equals to 2. So everyone can differentiate that. The rule is easy to get, but it's the domain we need to investigate. So the only point might not be differentiable is at x equals to 0. Agree with that? That's the connection point. That's the only point we might not be differentiable. So we need to investigate that point. So we first test about the continuity. When x equals to 0, x squared plus 2x plus 1 equals to 1. 2x plus 1 equals to 1. So it is continuous at x equals to 0. Okay, why we need to know this? Because if it's not continuous, why we talk about the differentiability? Directly not differentiable at that point. But it is continuous, then we need to talk about the differentiability. So what I would do, I would differentiate both graph, okay, left hand side and right hand side. That gives me 2x plus 2. d dx 2x plus 1 equals to 2. Okay, differentiate both function because I want to know the derivative of both function at x equals to 0. So when x equals to 0, 2x plus 2 equals to 2. So it is differentiable at x equals to 0 because the left hand side equals to the right hand side derivative and also is continuous. Therefore, it is differentiable at x equals to 0. Okay, it is differentiable at x equals to 0. So what my f dash x will be? My f dash, well, just derive the rule. That's 2x plus 2 and that's 2. And the domain, because x can be differentiated, so I will take the equal to 0. But I will only include equals to 0 once. You're not going to put greater equals to 0, less than or equals to 0. So where do you put the equal? Well, where the original function gets 0, you put the 0 at which function. So it's greater equals to 0 for the first function. So when the derivative function, we'll put 0 with the first derivative as well. So that's what we will do. Actually, it can give you same values. Doesn't matter where you put the 0, but it's more logical to put the domain same as before. Okay, same as before. But we did this only because we know x is differentiable. X can be not differentiable. Okay, so we don't need to include 0 at any function then. So if we try to sketch the f dash x graph, trying to sketch the f dash x graph. So less than 0, we have 2. And have 2x plus 2. Well, 0, 2 is still that point, and 1, 4 is here. I shouldn't have y here. I should have f dash x. dy dx or dy dx. So that's 1, 4, that's 0, 2. Maybe put another point, -1, 2, to say it's a horizontal line. Can see if it's differentiable at x equals to 0, that should be a continuous graph at x equals to 0. It's not going to be a jump. If there's a jump, which means you have different values for derivative at the same point. So there shouldn't be any jump. It should be continuous graph. Okay, it should be continuous graph. Okay, example 3. Example 3 is talk about, well, again, same question, talk about the differentiability for this function. And, well, let's say sketch f dash x as well. Let's sketch f dash x. Which point is not differentiable? Well, you definitely know it's not differentiable. The endpoints. What's the endpoints? -5 and 4. Okay, those 2 points is definitely not differentiable. Whether 0 is differentiable or not, it depends on the calculation. Okay, you need to investigate that. But the -5 and 4 is definitely not differentiable. So we test about the 0. Okay, we test about 0. We first talk about the continuity. So we say when x equals to 0, x squared plus 2x plus 1 equals to 1. X plus 1 equals to 1 as well. So is at x equals to 0 is continuous. Okay, because it's continuous, then we are going to talk about the differentiability. So d dx of the left hand side equals to 2x plus 2. d dx of the right hand side equals to 1. Well, that's the continuity. And then you say when x equals to 0, 2x plus 2 equals to 2, which not equivalent to 1. Okay, which not equivalent to 1. So at x equals to 0, not differentiable. Even though it's continuous, but left-hand side limit and right-hand side limit are not the same, then it's not differentiable. Okay, left-hand side limit and right-hand side derivative is not the same, so it's not differentiable. So what's your derivative rule looks like? The rule should look like 2x plus 2. When x belongs to 0 to 4 exclusive both ends, and then equals to 1. X belongs to -5 to 0 exclusive both ends as well. 0 is not differentiable and the 2 endpoints is not differentiable. So if you want to sketch for it, -5 to 0. -5 is here, 0 is here. We all got derivative at 1. But it's an open circle at 1 on both ends. Because you can't have derivative for -5 and 1. -5 and 0. So that's what you have. That's not the 5. That's 4. That's the origin. And from 0 to 4, you have 2x plus 2. So we have 0, 2 here. 4. Well, 10 is somewhere here. 10 is somewhere here, and 0, 2 is somewhere here. It's a straight line. That's 4 and 10. But it's open circle on both ends as well. It's an open circle on both ends as well. Can't differentiate endpoints and can't differentiate the connection point because left hand, well, you can see here, left hand side and right hand side derivative are not the same. One gives you 1 and the other one gives you 2. They are not continuous points. They are not continuous graph. So it's not differentiable at x equals to 0. The word smoothly joined or smoothly connected tells you that's a differentiable point. Okay? Smoothly connected or smoothly joined tells you that's a differentiable point. If it says this graph and this graph is smoothly connected or smoothly joined together, then it means it's differentiable. Okay, it's continuous and differentiable. Any questions about this? Alright, if we don't have any question, let's go to example 4, please. Read the question, please, and then write the derivative function for me. Okay, read the question and then show me what the derivative function looks like with the proper domain. Okay, with the proper domain. Okay, the original function looks like that, and what the derivative function looks like. Finish? I'll write the f dash x here. Okay, I'll write the f dash x here. Okay, what's the derivative for the first one? What do I have for the first one? What I should have? 2ax plus b. Okay, what's the domain? 0 to 3, inclusive or exclusive? Well, inclusive or exclusive 0? Exclusive, okay, because that's the end point. Okay, that's the last point of the graph. Exclusive. How about the 3? Inclusive, because it's joined smoothly. Okay, it's differentiable point. Okay, the join, all the points joined together is smooth point. So inclusive 3. Okay, what's the derivative for the next one? How do you find derivative for the next one? chain rule? Yeah, we can use chain rule. So what is it? Yeah, 2/3 times x minus 3. Okay, you put the 2, drag the 2 into the front, that's 2/3. Derive the bracket, that only gives you 1. And then you reduce the power by 1. Okay, it's still 3 things, but the 1 is missing. Because when you derive the bracket, it gives you 1. So we don't need to write it. Okay, x belongs to 3 to 4, inclusive or exclusive? 3 will be exclusive and 4 will be inclusive. You already include 3 in the previous function. You're not going to do it again in this function. You only take one x value once, okay, in a hybrid function. You can't get square bracket there. That's a wrong notation, okay, that's wrong. You only can take the value 3 in one equation. And we follow the original domain. Okay, what's the derivative for the last one? C. Okay, x belongs to 4 to infinity, inclusive or exclusive? Exclusive, both one. Well, 4 is exclusive because it's take 4 already in the previous one. Okay, that's the derivative function, what the derivative function should look like. And now, well, function 1 and 2 is connected at x equals to 3, right? And function 2 and 3 is connected at x equals to 4. So that's like one function, 2 functions, 3 functions, and join at 2 different points. Okay, join at 2 different points. A third x minus 3 squared is the middle function. Okay, it's the middle function. Join smoothly will give you 2 pieces of information. First, they join. They join. Second is smoothly. Well, different, like gradient the same, derivative the same, derivative equal. Okay, derivative equal. Derivative equal on left hand side and right hand side of the same point. So that's, well, basically it's continuous and differentiable. Okay, basic tells you is continuous and differentiable. Then according to all of this information, I know first of all they need to join together. Okay, they need to join together at 3 and at 4. So when x equals to 3, 9a plus 3b plus 9 should equals to a third 3 minus 3 squared. Right? That's, they join together. They join together. So what I have, that's a 0. Okay, this is a 0. So 3a plus b plus 3 equals to 0. You divide 3 on both sides, so you have 0. That's a 0. When x, when x equals to 4, then a third 4 minus 3 squared should equals to 4c plus d. So a third equals to 4c plus d. That's when they are continuous at x equals to 3 and 4. Okay, it's continuous at 3 and 4. That's joined. And then the smoothly gives us the derivative are the same. When x equals to 3, derivative are the same, is 2a times 3 plus b equals to 2 over 3, 3 minus 3. Two function, well, now we look at the derivative function. The derivative for 3 should be the same on the left hand side and right hand side. Then 6a plus b should give you 0. Well, I have 3a plus b gives me negative 3. And then when x equals to 4, the derivative will be the same again. So 2 over 3, 4 minus 3 equals to c. Because the derivative left hand side and right hand side must be the same. So for this function and this function, they are equivalent. So it's a constant, so c. So c equals to 2 over 3. Well, d equals to a third minus 4c. d equals to a third minus 8 over 3. d equals to negative 7 over 3. I've solved C and D. And for A and B, well, we have two simultaneous equations, 6a plus b equals to 0 from the top and 3a plus b equals to negative 3. Then we subtract them. I have 3a equals to 3 and a equals to 1. And b equals to minus 6a, b equals to negative 6. It's the solving from the above step. A plus b equals to 0. On that side we have 9a plus 3b plus 9 equals to 0. 3 plus b plus 3 equals to 0. Okay, so that's how we solve out the two values a, b, c, and d. Okay, so by drawing smoothly, so you need to understand what drawing smoothly means. Alright, so I have a couple of minutes here. So if we can go back to the first example, okay, if we can go back to the first example, we have like two functions, which is like the hybrid function y equals to x and y equals to minus x. If we can sketch for that, that's y equals to x when x greater or equals to 0, and that's y equals to minus x. That's when x less than or equals to 0. That's the point 0, 0. It's continuous. Okay, it's continuous. But which point do you think is not differentiable? Where? Origin x equals to 0 is not differentiable because negative 1, positive 1 as the gradient, right? Negative 1, positive 1 as the gradient. So sketch a graph for a suitable domain. Well, I have draw it and then talk about the differentiability. It's not differentiable at x equals to 0, but it's differentiable at any other point. Okay, just that, not that point. So if I can sketch a derivative graph, f dash x, that's f(x). Well, right hand side is positive 1 as the gradient. Negative 1 on the left hand side. It's constant because it's linear. So that's 0, 1, 0, negative 1, but it's open circle for both function because it's not joined together, therefore it's not differentiable at that point. Okay, left hand side and right hand side limit are different. So that's the derivative function. It's not differentiable at x equals to 0. But anywhere else is fine. Okay, anywhere else is fine. Alright, that's the end of differentiability exercise. I'll save that. Well, that's the end of the chapter. That's the last exercise.